Hello everyone, today I'm going to deliver another lecture which is earthquake resistance design of steel structure. The topics will be covered first failure mode and destruction of earthquake, and then basic structural topography, and it will contain moment resistance frame and concentrically bracing frame, eccentrically bracing frame, and then code-based seismic design profession, which is a special moment frame, international intermediate moment frame, ordinary moment frame, and special moment frame, and then design of beam column, and then modify a beam action, which is reduce beam section, and then column beam ratio, and then bracing of beam, and then design of beam column connection, and then weld factor, and then continuity of plate, and then plate zone of beam to column connection, and last one is practice problem of steel structure. So it will be all other theoretical theory other than this practice problem. So all these are theory, and last one is a example. So let's start. Okay, so I'm taking um, okay, I'm taking a note. This taking the note is taking from Professor Dr. Yuktika Ranam sir, University of Asia Pacific, Bangladesh. Okay, so let's see. At first, we've been seeing the failure and distress of steel structure during the earthquake. Steel structure have always been considered a suitable situation for construction highly seismicity area due to high strength and durability, ductility exhibited by structural materials and highly ductile assurance. In spite of this natural advantage and resources, uh, concern out of the necessary necessity that special care must be paid in order to ensure the ductile structural behavior, as the conformation steel moment frame building exhibit the unexpected fatigue behavior during the seismic event of Northridge and Kobe, which is 1994 and 1995. So we have been seeing here lots of the uh, um, figure 1, that this steel frame is suffered large permanent deformation. There was no lateral bracing, and connection detailing was inadequate. Okay, another picture we've been seeing here, the rectangular column suffered local buckling here at its foot, and resulting cracking of the coiling point invisible. Another picture we've been seeing, there is a white crack at the bottom of the main frame column. Possible causes include the high cyclic or normal load. We have been seen here, and this is also here in zooming. And the high strain rate in material defect and weld effect and thermal stresses. So another example we've been seeing, the diagonal element with broad flange cross section have buckle about their weak axis and have broken. We've been seeing here. This is also buckle, and another figure we've been seeing, truss element have truss element have buckle and damage locally here. We've been seeing. Okay. We've been seeing the weld between column and beam failed in resulting with crack. This is the crack, and bolt failure in this beam column connection. In this beam column connection, bolt is failure. Okay, so I hope that on this are the indent. So another is basic structural topography, which is content moment resistance frame, and concentrically braced frame and eccentrically braced frame. Okay, let's start. The basic structural topography. The main topography of seismic resistance is dissipated structural can be classified in and dissipated element. Three different topological can be recognized. Moment resistance frame are the rectilinear assembled beam and column with the beam rigidly connected with column. This is the moment resistance frame, beam and column, uh, and with beam rigidly connected. So these are the rigidly connected. This beam column are rigidly connected. Okay, we can see the concentrically braced frame, which is CBF. Uh, the resist the lateral load partially by developing high axial forces in diagonal member. So this is the cross section of bracing we can see here, concentrically bracing. This is concentrically bracing frame. Another is eccentrically braced frame we have been seen. This is eccentrically, so this is not from here, rather than it is taken from here. Okay. This whole earthquake creation is still structure we can use. If the bracing, then the structure will be resisted due to earthquake. Okay, so I think these are completed, and now we'll go the code-based seismic design provision, which is special moment frame, intermediate moment frame, ordinary and special moment frame. Okay, let's see the special moment frame, which is SMF, are the considered the most ductile three type of moment frame considered by AISC for reason due to their architectural visual. SMF have been most popular seismic farming system, highly seismic region under USA and Bangladesh also in others region. Okay, so SMF are designed to earthquake load calculating using value of R equal to 8. So this is the main point where the R value of will be 8. Okay, so another see the intermediate moment frame, and we have to see beam column connection SMRF the required have minimum inelastic rotational capacity 0.4 radian. So the and the intermediate moment frame we have been seen are assumed to be less ductile than a special moment frame, are expected to do with Eastern modern inelastic deformation region earthquake. SMRF design using a value of 6. So we have been seen the special is 8 and there is a 6. So it is decreases from the previous. And we have been seen the beam to column connection SMR the required to have inelastic rotation capacity 0.02 ratio. And in the ordinary moment frame are less ductile than intermediate moment frame. So if we see the value of R is 4, so it is less than also intermediate moment frame and the special moment frame. So we can mark is in yellow color. Okay, so on this are the completed. Now we have been seeing design of beam column. So special frame, we have been seeing the special moment frame. Special moment frame. These are the special moment frame. Design of beam column. A beam is still special moment frame is assumed to be able to develop is full plastic, which is MP equal to Z Fy. Z is the plastic section modulus and Fy the we know the steel yielding stress. And we know the in addition the flange of beam must be lateral brace and potentially hinge, and unbraced length of the beam must not exceed 250 Ry divided by Fy. Ry is the radius of gyration in weak axis out of plane blocking. So we've been seeing the limitation width to thickness ratio. These are the important. We've been seeing the flange of I shape of beam channel is flexure B divided by T, and then omega B will go 65 into Fy, and PS equal to this below. And web of I shape of beam combined and flexure and axial stress is divided by T of web. It will be this. If the condition is satisfied, then we will use this formula. If this condition is satisfied, we will use this formula. And for lambda by PS, if the condition is satisfied, then we will go this formula, otherwise this formula. And round edges and axial, these are not frequent use, as we have mentioned. The I shape is frequent use for wire flange and wire. Okay. So here the inlet. Now we'll go to the modified beam section, which is reduced beam section. Here is a modified beam section. As the reduced beam section is concept is a trim beam flange near connection. We've been seeing a value is 0.5 to 0.7 BF. P is given 0.85 to 85 dB, and C equal to B by 6. And reduced moment at connection, we've been seeing at connection, and force plastic hinge from the connection. This is the connection, and this is the reduced section. And the reduced section, we've been seeing a reduced section of beam. We've been seeing here is denoted by B, and A is we can see the length distance up to reduced beam section. This is the protection zone. Okay, so modified reduced beam section is given here. So unbolted, unsatisfied, and stiffness extended into plate. Bolted, unstiffened, and stiffened extend in plate connection. We can see here bolt, unstiffened, and stiffened extended in plate connection. Here is a 4 bolt unstiffened, which is 4E. We can see here. As a 4 bolt is stiffened, this is the stiffened. We can use it stiffened. Here is a 8 bolt stiffened ATS. We can see the stiffened is not only here but also stiffened is here also. If we use a stiffener, then the section will be more stiffened. Okay, so this lecture also completed here. Column beam moment ratio. Now we're going to column moment ratio. We've been seeing here PC greater than PP, and found this below, and computing this right beam, and this is the left beam, and this is the column, and given this plastic moment of the beam column, we can see here, and this is the column. We can see this is the also column. And lateral bracing, we have been seeing another topic is lateral. Okay, these are the complete and lateral bracing of the beam. So we have been seeing lateral bracing of the beam. Lateral torsional buckling controlled by LB divided by LY. LB is the distance between beam lateral brace, and RY is the weak axis of the gyration. These are the picture. So LB is given this formula, RY is given, and LB will be 100 into 25. So lateral torsional buckling and bracing we can see here. Okay, so let's see another design of beam column connection. As a design of beam column connection, this is beam and this is the column. The weld flange bolt web moment connection widely used early 1970 to 1954. We've been seeing here the performance of the pre-1994 joint of cyclic loading. We've been seeing here. This is the cyclic data, and drift angle divided by bending moment, and the load is going this way, push and pull way. The beam column shall be satisfied from this point, and the weld factor. Now we'll go and these are the completed, so we'll go to the weld factor. This is the weld factor. Most common pre-Northridge weld electrolyte had very low factor tough, typically chirpy P notch, which is less than 5 feet LB at 700 feet. Require the minimum toughness of oil to metal is required CV, and these are the requirement oil factor. Okay, so now we see the continuity of plate. This is the continuity of plate. We have been seeing lots of the figure, the continuity of plate within joint. So if we firstly represent continuity plate is given here, but we can say that this is the stiffener. The continuity plate is here. The continue will be here for getting the more stiffness. The oil flange column we have been seen here. The continuity is given here. Continuity plate is required unless this condition is fulfilled and this condition will fulfill. So this is the given here. Okay, so this is the last theory, which is panel zone of beam column connection. Okay, we have been seeing panel zone and beam column connection. This is the panel zone, and this is the column, and this is the beam. Okay, let's see here the shear strength PP equal to given this equation as M. All the are opposite direction, anti-clockwise. M1 is anti-clockwise, M2 also anti-clockwise, and B2 is the opposite. It is also the same direction. M1 and B1 is also same direction. Okay, so we have been seeing another depth of the beam of the equal depth, which is given this formula. Panel zoom thickness and double plate is given this formula. The option of oil double plate we have been seeing here. This is the double plate. Okay, so now we'll go to the practice problem of earthquake resistance design of steel structure. These are the main important. So let's go there. Okay, these are the problem we have been seeing here. The question is given. At first figure is floor plan. I am going to here. Okay, F1 figure 1 shown in floor plan is 6 stories building. Whose beam column section is given figure 2. This is the figure 2. Okay, figure 2 is given here, and assume P equal to 0 for beam and 3 kips per column, and calculate PB, which is given the formula MPR, which is given also a formula for beam MPR, and checks the width thickness ratio of flange by this equation, and calculate the space of lateral bracing by this equation. Okay, let's start. At first we are calculating, we know the some wire thickness and flange thickness. We know some wire thickness and flange thickness is given here. So beam, we know B1 is 4 is given, and H1 is, we are taking full, this full, and B2 is also 4 minus 0.27, this 0.27, and H2 is 7 into 1/4. So we are taking RY is 1 because we are find this from FY of steel, building of steel. So let's see, ZB equal to full minus hollow. So this will be full, this will be full, so it will be rectangular, which is B h square divided by 4 minus this shadow, and P h square divided by 2. In this way we are finding here ZB, and PMPB will be ZBFY, ZB is found here and FY is given. RP which is 1.1, RY we are taking 1 because we are thinking that we are taking from this test. For column AG equal to full minus hollow, this is the full and the hollow section is a void section, and full we know 8.822 have been seen here, and minus hollow section we have been found 7.71 minus 6.68. Okay, how will get this? This is the section we've been seen here for column section, and this is the B 8.22, H1 is also 8.22 for full, and hollow or void section we've been seen 7.71 and H2 6.62. We're taking this information here, and in this way we've been found 16.668. That sheet which is full divided by void or hollow, and found 15, putting all these below and found 54.89. So PUB equal to UDL load into tributary length into number of stories. So UDL equal to 2 and tributary length we have been found 15 into 15 and number of stories is 6. I will get we know here this is 15, this is 15. So if we consider this beam or this column, then it will be tributary length of this. So this will be 15 and this will be 15 also. And UDL is 2. It is given. And number of stories 6 we have been shown, and MCB equal to using this formula and found 84.3. Okay, so first we have been checking here MBP and MCP. We have been found MB for beam, plastic moment of beam. We have been found plastic moment of beam where this plastic moment of beam we have been found here, and we have been found plastic moment for column which is 84. But we have been found beam is 54, beam is less, and column is taking more. Okay, so let's solve the second, which checks the wide thickness plan. So we've been checking here B into divided by BF, which is B. B means this divided by 2, 8 divided by. This is the wall total section is 8, and it will be 4 divided by 2, and BF is given. Flange TF is the thickness of flange, and found this below. For column flange we have been found B into TF, and putting this information in 5.07, and lambda P is C in 8.82. So 8.82 is greater than this below, which is okay, and 8.22 is greater than also B into TF is okay. So now we are beam web. We can see here H divided by TF is 29.6, and for beam we have been found 82.2 using the formula. So we have been seen 82.2 is greater than 29, so this is also okay. So now we have been seen for column web H divided by TS found 16.1, and PY equal to FY AG. AG will be column. This is found 16.68 in previously. We have been calculating 16.68. This for column, and found 667.2, and using lambda, using this equation, and putting 5 PY. 5 PY is the total value of 5 PY. Remember it. There is no reduction factor, and 47.1. And another check is at 253 root over pi, which is 40. So we've been seen here the 47. We've been here 47 is greater than 16.1. Is found from here. Is also this formula we've been used found 40 is greater than 16.1. So it is okay. So all is okay. We've been seeing all the type is okay. So if we not okay, then we can increase the thickness. If we found the not okay, then increase for thickness or width or height or material strength FMC. But we basically increasing the thickness, then the wall will be fine. So these are the index. So another, calculate the spacing of lateral bracing here. So let's see here. A beam which is found B1 H1 B2 H2 and found 15.93. This is for beam. And also IB, we have been in I1 I2 and found 5.59 inches square. Radius we have been in RY, which is taken in previously, which is 9.82 as also near here. Spacing of lateral bracing LB equal to 2500 FY equal to RY. R was taken 0.92, found 58. So we have been found the calculating spacing 58, so 58 inches square. So let's see another example. Calculate the, this is the two, calculate the shear force for capacity B beam using this formula. So we are using this formula for beam. We have been found to 22.7 as we have been 50 we have been used the moment 54 for beam, and LB equal to 15. By 15 we have been found the 58, but we have been seeing 3 into 58, which is 45. It's close to 45. That's why we have been used 15. This column, the moment we have been used from column we have been found, and previously we have been seeing here. At first we have been found beam moment of beam is 54, and column, where is column? This is the column, which is 84.3. So basically we are using this 83.4, and in this way we have been found here. So another, calculate the distance essays using this formula from face to beam plastic hinge. So using this formula and found 8.84. And A we have been, so it can another, we have been seen compute and compare MP using this in this formula. Okay. So MP of beam, we have been calculating this formula and found 82.7. So ASIS we have been found 8.11, and this is the 8.11 we have been used, and divided by 2, 12 as it is taken to feet, and 8.22 also taken also feet. M column we have been found 89.88. So we have been seen the column is greater than B, so we can see strong column with beam, so it is okay. Okay, this is okay. So let's see number 3. Here's the number 3. You can see the horizontal shear force of the plane is given this formula. We can see here B1 all the beam 54.8, the beam moment, and TB is given here, and neglect B. Horizontal shearing force of the panel we have been seen using this formula. B1 B2 is all are the same, and found 172. So these are the index. Another is a nominal shear strength of panel RB using this formula. So maximum of 1 into this formula, and found 1.27. Using this formula, PY equal to 67.2, and FU have been found 36, which is UTL trajectory area, and number of stories is taken here. So 1.21, but we are taking the, as it is greater than 1, but we are taking 1. So nominal shear strength of the panel, we are using this formula, which is maximum 1 or 2, and found 149.1. So we've been seeing the capacity 1419 is, but applied is 172. So these are the not okay. So how will, what is the remedy, what is the solution? We have to increase the column thickness TW and material strength. So I will get this as the TW. If we increase TW, we will find TW is 0.51. So we have to increase this. Okay, these are the complete. So another is determine the require of the joint continuity plate using this equation. So we are using this equation and found this um, and found this, and if we use this formula and found 0.667, and column flange thickness we have been known 0.481. So 0.81 is greater than 0.701, and also 0.81 also greater than 0.601. So these are the okay. So we don't need using continuity plate. Okay, so let's see another the possible thickness joint continuity plate using this formula. Okay, so it is the provide the possible thickness of joint continuity plate at the exterior joint using this, and interior joint using this point. Exterior joint using this formula. So use this formula 1.213, and exterior using this formula 1.426. Okay, and these are the inlet. Okay, we can see another example is 5, which is the calculate the appropriate dimension of the reduced section RBS. Is we can use the A and B. So let's see using A, which is 2.4, and B equal to 6. Now we can see cut, which is C, using this formula. S is the distance from face of the column point of the inflection beam. So C is found is 1 inch, and reduced section are cut 5 inches square. Okay, so it is completed. So now see another example. We are also seeing this example, which is we can solve the earthquake resistance design of steel structure. Okay. We can see the member of the section is given figure 1 and model 1. This is the figure 1, this is the model 1. Given below, assume the distributed load 3 kg per feet over the beam length, and calculate the horizontal shear force as well as the nominal shear strength RB and the plane zone beam column joint. Determine the required joint continuity plate and it is possible thickness at the exterior joint and interior joint. Okay, this is beam section, this is column section, this is the model 1. Okay, so let's see here. We can see for beam information we are taking from beam information, and we can see here full divided by hollow means void, and found 21.59, and for a moment beam we have been used this formula and found 71.90. So here we can use this formula and found there is no applied load, that's why PC equal to 0, and found 204 kip. So PU we know ideal into tributary length and the number of stories, and found 1080. So we know also PU equal to FIAG of column, and found 2494 kip. So minimum we are taking 1, or this formula which is 1.31. We are taking the 1, and RB we using this formula and found for calculation of RB. We can see here RB using this formula and found 175 kip. So we have applied 204, but we have a capacity 175. So this is not okay. So what is the solution? So solution is increase the column thickness TW and material strength Fi. So if we increase the TW, then it will be increased, and then 170 Fi also increase. So in this way we can solve this problem. So let's see the solution of 2. What is the solution? Determine the required joint continuity plate and it is the thickness. Okay, so let's see the requirement. You can see here 0.73 we've been using all. Ry is always 1. Ry is always 1. Okay, so 0.76 and bf divided by 6 is the 0.75 and tf equal to 0.9. So we have been seen 0.9 is greater than 0.76 and 0.9 also 0.75. So these are the okay. So there is no needed the continuity plate. So another one, if the possible if it provide possible thickness of joint continuity plate at exterior 0.225, at joint which is 0.45. So these are the in-depth. If you have any question, then let me know. I will try to convince you. I'll try to answer your question. These are the basically theoretical question, a theoretical part. But last part was the main example, which is called earthquake resistance design of steel. If you have, then ask me. I will try to convince you. Okay, this is the theoretical, and last one is a practical. So let me know if you have any queries. I want to clarify you, and all the information is given here. So I think if you calculate deeply and pausely the video, then you can calculate all of the things. Please subscribe my channel and give me the what I will say, like button. Thank you.